Hello. Hello, hello, hello. All right. It's Friday. We got one more day to go before the weekend. Because we're still keeping track of time. Even in these circumstances. Okay? So, hopefully everyone is alright. Hopefully everyone is good and ready and raring to go. And we're going to be taking a look at some exponential and possibly some logarithmic differentiation. Okay, we're going to stick with differentiation today. We're going to look a little bit more about perhaps the integration part of things in a separate video. Okay. And the first thing that we're going to do is we're going to start off with the exponential side of things. Okay. So, with the exponential side of things, it's always a good idea to kind of remind ourselves as to what that word exponential actually means. Okay, because the maths of what it is comes from the from the word. Okay, now the actual word for exponential means that the rate of change at any point is proportional to the value that it already is. Okay, so that just means that if you've got more of something, the faster it's going to grow. The less of something you have, the less quickly it's going to grow. Okay, it could also mean that the kind of inverse of that as well. Okay, so if you're talking about like a negative exponential, that the more of something that you have, the slower it's going to grow, or whatever. Okay, it just means that it's proportional to the amount of whatever it is you have. Okay, and without directly referring to a particular disease that's going around at the moment, wanted to kind of show you a GIF which actually isn't about that particular disease, but it's about E. coli instead. And you'll notice that when I hit play, that to start off with, it doesn't actually grow very quickly. But once it starts to get past a particular point, it starts growing very quickly indeed. So just have a look at this. They're growing quite small amounts. Okay, there's not a lot of it. It's growing quite slowly. The more there is of it, the quicker it speeds up, and then suddenly it grows a lot very, very quickly. Okay, the time scale in that doesn't change. It continues to go up 2 minutes in every frame. Okay, and there we go. Especially around the 260-minute mark, it starts to boom. Okay. And this kind of exponential that we associate with kind of exponential growth, disease control, and things like that. Okay, so that's enough of that. So we're going to think about what that means. Okay, so the rate of change, and remember that's what a differential is. A differential shows us a rate of change. So for a function e to the x, its derivative, okay, or its rate of change, so dy by dx or f primed of x, is going to be proportional to the value, the function at a particular value. So we could say that it's proportional to whatever that is. Okay. Now, the power that we have will determine what kind of proportionality we have, whether we have just a straight equality, or whether we have something like a number times e to the power of x. Okay, or we could also have that for a different function, which is a to the x, just like a number to the power of x, that I nearly wrote f, g primed of x is proportional to a to the power of x. And one thing that we'll have to think about is what that constant will be, okay, or what will jump down the front of our exponential to make it proportional, okay? So our first kind of keynote for what we're going to need, if we've got just a straight up normal exponential, then what we actually get is that the rate of change, dy by dx, is e to the power of x, okay? If we have a straightforward exponential graph, then we have the gradient, the derivative, being exactly the same at that point, okay? So if we were looking at when x is equal to 2, the derivative would have the same value as the y value that it currently has. That makes sense. We can generalize this, which is good. We can generalize that to say that if we've got y is equal to e to the, like, a function of x, then dy by dx will be the function differentiated times by e to the function of the x, okay? So just as a quick example of what we mean by that second one, the one that's kind of off over that way, if we had e to the power of 3x plus 4, and we wanted to find dy by dx, then we would differentiate the function of x, that's the power, so 3x plus 4 differentiated is just 3, e to the power of 3x plus 4. One important thing to note is that the power of our exponential does not change, okay? That's one important thing for us to be aware of, okay? Now, the other thing that we're going to be taking a look at is the logarithm side of things, okay? The natural logs, or luns, okay? Now, this one is a little bit more kind of awkward to think of in terms of just pure words, but what we will actually find, and there are ways of thinking about this, and I'm going to send out a resource that will kind of show you it stage by stage in a first principles. I'm not going to go through that here. We actually get that the derivative is equal to 1 over x. Excuse me a minute. Okay, so we get that dy by dx is equal to 1 over x. Okay, again, we can generalize this, and these generalizations are really important. They will help us speed up some of our differentiation and integration later on. Okay, so if we have the y is ln of a function of x, then dy by dx will be the derivative of that function over the normal function, okay, the function as it was, okay? And just doing a quick example for the logs, let's say that we've got a function which says that y equals ln 2x squared plus 4x. Then dy by dx, we get the fraction. The denominator will be what that function of x was. Okay. And the numerator will be the derivative of that function. So the derivative of this. So the derivative of 2x squared is 4x, and the derivative of 4x is 4. Okay? Now, both of those things are things that you will absolutely need to know off by heart. You'll need to be able to recognize them. You'll need to be able to spot them when they occur in differential equations later on. You'll need to be able to spot them in terms of integrating and different methods of integration later on as well. It is in your absolute best interest to know those things inside out and to be able to spot them from getting up to a mile away, okay? We absolutely need those things. Now, at this point in a lesson, I'd be throwing out some whiteboards and going, okay, let's see what we can make on some of these, okay? And what I will kind of let you do is just kind of pause the video at this point, have a go at some of these questions and see how you do with them, okay? What I will do is I will come back to this slide at the end of the video and put up some answers to these at that point, okay? I'm going to look to try and keep things moving while I can. So I'll come back to this at the end and give you guys some answers for this towards the end, okay? So we've got our general rules for dealing with exponentials and logarithms. Okay, we had them as those big red box notes from before. So differentiating an exponential is exactly the same as it was before. Okay, the rate of change of an exponential is its value at that point. The derivative of sine k of x. Now, this is a little bit of memory jogging from a previous video. Remember what happened to that k? That k gets that inside bracket got differentiated and brought to the front of our sine function. I'm struggling to be able to speak. So we'd get k cos kx. So thinking about what would happen here, we said that the derivative of that power comes to the front of our exponential. So I should get k e to the kx. Okay, and that's where some of this proportionality comes into play, okay? That's where some of our multiples come into it. Now, d by dx of ln x, little bit of a memory test for you. What did the ln differentiate to? The ln differentiates to 1 over x. So thinking about what ln kx would differentiate to, just give you maybe 30 seconds to have a think. If you had ln kx, what would that differentiate to? Should it be simplified? Okay, have 30 seconds to think about it. Alright, so if you had ln kx, you may have remembered that the derivative of the ln function goes to the top over the original one. Now, when that simplifies, what we get is just 1 over x, okay? Because what we get for the ln kx is that we would have k over kx. Okay, and the two constants would have to cancel each other out, so we're just left with 1 over x. Okay, it's important to note that if you just got a number times your variable inside a ln, that those constants will cancel each other out. Okay, even if you get to this stage, okay, that is still useful because you can still recognize that the constants will cancel each other out. Okay, now this, where we have a to the power of x, this is something that in my experience often gets overlooked. Okay, e to the power of x, kind of, we just had e to the power of x as its derivative, but for a to the power of x, we get something slightly different. Okay, what we get is that it's still proportional to itself at a particular value, so it's still going to be something times a to the power of x, but what that something is that it's ln of a. Okay, and if we just take this back to thinking about our e to the x, when we do d by dx of e to the x, what we should actually get is e to the x ln of e. But if you know your exponentials and logarithms, when you take ln of e, that is just equal to 1 because they are inverses of one another. Okay, so that's why we don't think about that ln e at the end. It just kind of disappears. So this thing here is what I think often gets a little bit overlooked. We do need to remember that that is like our kind of constant related thing. Okay, so d by dx of a to the power of x is equal to a to the power of x times ln a. And we could kind of combine that with the stuff that we had when we had e to the power of kx to think about this and just compound it that little bit more. Okay, normally so if it was just a to the power of x, we'd have a to the power of x ln a. But now, because we've got a to the power of kx, we're going to have a to the power of kx as part of our answer. We're going to have ln a because of the different base. And we're also going to have the k because of the fact that when we differentiate some kind of exponential function, the derivative of the power comes down to the front of the function. Okay, and there's an awful lot of information going on that screen. Okay, and an awful lot of things that we should look to try and be careful of, be wary of, and be considerate about. What are the things that I would say we must absolutely recognize and know? We must absolutely recognize this at the top right, so that d by dx of e to the kx is k e to the kx. We must absolutely know that d by dx of ln x is 1 over x. Okay, and we should be at least very aware that if we have a to the power of x, that we must insert this constant of ln a. Okay, so yeah, there is a lot going on that page. There is a lot of information there for us to be wary of and be thinking about. Okay, now at this point I would suggest heavily making some notes on this screen, perhaps making a couple of flashcards on this screen, something that you can test yourself on and look to kind of try improving your memory about. Okay, especially the key facts that I mentioned before, the e to the f of x one, and also the ln ones as well. These boxes summarize that quite nicely. These ones go into the kind of the nuts and bolts and the little gritty details of it. So, at this point, hopefully you've made what notes that you need, thought about what you want to add in terms of your kind of flashcards, your knowledge, and all those kinds of things. Now is the time to look to try and put it into practice. Okay. So here are a series of questions which, when you get used to your differentiation of exponentials and logarithms, these you should be able to just reel off real quick. Okay, but because we're just getting used to it, things may take a little bit more time. Okay, we got what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, including our meteor example, different questions. Okay, so I'm going to give you about 8 minutes. So I would think give yourself about 8 minutes to have a go at this. Okay. Set yourself a little timer, put a timer on your phone, that kind of thing. Give yourself that 8 minutes to have a go at these questions, okay? And see if you can get the right things going in the right places, okay? I'm not going to count down those 8 minutes at this point, okay? But look to give you about those 8 minutes. I'm going to just give a little pause so that people can pause the video, and then I'm going to push on and go through some of these answers so that we can, see some of these things in action. Okay, so time to pause is now. Okay, so at this point, hopefully you've had a go at some of those questions. You've had a go at getting some of these answers together, the mixing in some of the things which we should know already. Excuse me. So let's have a look at some of these answers. 3 to the power of x. It's not e to the power of x, it's a number to the power of x. So this is where we should have like 3 to the power of x times ln of the base. So we should have ln 3, 3 to the power of x. Okay, which we do. This isn't an exponential, this is just a cubic. Okay, so we want to do x to the power of 3, the power decreases by 1, and we times by the old power. So it's just 3x squared. That's one that we should just know. Ln 3 of x, okay? Now you may have written 3 over 3x, which would be an unsimplified answer, yes, but remember that it will just simplify to be 1 over x, because the 3's will cancel each other out. 3 to the power of 2x, that's kind of like this one here, but because I've got a function of x as my power, that means that I have to differentiate that function and multiply by it as well. So I'm going to have 3 to the power of 2x, ln 3, because of the different base, times by 2. Okay, so 3 to the power of 2x times by 2 times by ln 3. Slightly different variation here, but similar things. We're going to have the 2's and the 3's in the different places. Essentially, the 2's and 3's are going to swap. 5 times ln x. Now, you've got a constant times by a function. And when you have a constant times by a function, so let's say that you wanted to find d by dx of a f of x, that would be the same as just bringing the constant out of the outside and doing d by dx of your function. So I'm going to get 5 times the derivative of ln x. 5 times 1 over x is 5 over x. Okay. We'll do this one and then we'll pick and choose a few more just so that we go through, and then I'll reveal all the others. So this is an exponential with a function of x. So we differentiate the function of x, just give us a half, multiply by that. The ln doesn't feature in this because when we take ln of e, we just get 1. So it's as though it's not there. Let's have a look. This one here, d by dx of 5 lots of 4 to the x. Now, a classic mistake would be to do 5 times 4. Okay? and then look to differentiate it. No, absolutely not. We cannot do that, okay? This is 5 lots of 4 to the x, okay? It's like this thing here, where the constant is 5, and the function of x is 4 to the power of x. So I differentiate the f of x, okay? So that's like one of these right at the top, and then times it by 5. So the differential of 4 to the power of x is going to be ln 4 to the power of x, and then we times it all by 5. 3e to the 2x, so we're going to pick and choose a few of them now. This one is a function of e, so I'm going to have the derivative of 2x, which is just 2, times it by 3, we get 6, so I get 6, and then e to the 2x, because the actual exponential part of things doesn't change. I think that's pretty much... The only thing with this very last one is just be careful of the negative. When you differentiate negative x, you get negative 1. Okay, so that's going to be negative e to the negative x. And when you get into exponential forms of complex numbers, you will get e's to the x's and negative e to the negative x's as well. So, you know, thinking about that might be useful later on. Just be careful of where those negatives go. Okay, we'll reveal all the others. Okay. Now, this meteor example is where we're going to finish. Okay, and we're thinking about population models. There are some great examples of maths linking them with biology to do with differentiation and integration and exponential growth and things like that. Yeah, there was a whole unit at university that I didn't do, which was called mathematical biology. Okay, which was all to do with differential equations of how biology and animals and populations grow and how they all interlink. And we'll see a little bit of that when it comes to modelling with differential equations, but this is kind of like a taster, or a little kind of, warm-up of an idea. So we've got a rabbit population, which can be modelled using p equals 1,000 lots of 2 to the power of t. Determine after how many years the rate of population increase, which will reach 20,000 rabbits per year. So we want the rate of increase equals 20,000. That key word, rate of increase, a rate is a rate. Hang on, a rate is a rate? Yeah, a rate is thinking about how something changes with respect to time. So in this case, it's thinking about how our population changes with respect to time. dp by dt. Differentiate this. Now I'm going to have 1,000, because that's just a number. Differentiate 2 to the power of t with respect to t. So I'm going to get 2 to the power of t, because that's like the exponential part of things. Now we don't have an e as our base, so I'm going to have ln 2. So I've got 1,000 times 2 to the power of t times ln 2, or 1,000 ln 2 times 2 to the power of t. Now we want to know when the rate of increase reaches 20,000. Okay, so it just means that in the next year it will have grown by that amount. So we want to find out our value of t. First thing to do is to look to divide by that constant. Okay, and that will equal 2 to the power of t. So we've got 20,000 divided by ln 2 times 1,000, or that will just simplify to 20 over ln 2, is equal to 2 to the power of t. Now, if you know your logarithms, and you know them well, then we're going to want to take a log of both sides, but we're going to take want to take log base 2 in order to get our value of t. Okay, we don't really want to have to plug and play different numbers of t to find out what that is. We want to do it mathematically when we want to do it properly. So I want to do log base 2 of 20 over ln 2, which will equal t. Okay, and my calculator, got my old one. So let's type it in. We've got log base 2 of 20 over ln 2. We get 4.85. Okay, and there we go. Okay, so I think that is as reasonable a place to leave it for the moment. Okay, we've thought about differentiation and integration of, no, not and integration. We've thought about differentiation of exponentials and logarithms. Okay, now answers to some of these. Okay, I'm gonna rattle them off quickly. I'm going to write them down as I go so that if you miss them out, then you can see them still written down. So 1a, we just get e to the x. B, we get 3e to the x. C, we get 1 over x. And D, we get half of 1 over x, which is just 1 over 2x. Question 2, differentiate with respect to t. So the constant disappears, we just get negative 2e to the t. B, we're going to get 6t plus 1 over t. C, we get e to the t plus 5t to the power of 4. And it's important that you don't get your exponentials mixed up with just a regular differentiation like you would have seen in year 1 or your AS maths, okay? Next one, 3 over 2t to the power of 1/2 plus 2e to the t. 2 over t plus, now square root of t is the same as t to the power of half, which is going to be 1/2 t to the power of negative 1/2. F, 2.5 e to the t. Take away 3.5, which is same as 7 over 2 times 1 over t, which we can write just as easily as 2.5 e to the t minus 7 over 2t. G, differentiate 1 over t, so that's the same as t to the power of negative 1, so that's going to be negative t to the power of negative 2 plus 8 over t. And then the last one, we've got 14t minus 2 plus 4e to the t. Whew. I say, if you can get up to that kind of level of fluency with your differentiating exponentials and logarithms, that's great. That's a really useful thing to be able to have, especially moving forward and dealing with things like differential equations and so on. So I'm going to leave it there. And if you want to go ahead and do a little bit more practice, there is a textbook location for you. But yeah, make sure that you can commit some of these rules to memory. It will make things a lot easier for you later on. I will see you in another video. I will see you next week. Ta-ra.